For 40 years, exactly one company on Earth has controlled the machine that makes every advanced computer chip possible. Not a handful of companies. 1. A single Dutch manufacturer holding a complete monopoly over the most important piece of industrial equipment on the planet. In 2019, the United States convinced that company to cut China off entirely, betting that without this one machine, China's chip industry would simply stall out. In November of 2025, a desktop-sized device inside a Chinese lab used a technique that company had already tried and thrown away, and used it to etch a working 14-nanometer chip. Not a simulation, not a theoretical paper. A real chip, etched using extreme ultraviolet light generated by a method the world's only EUV supplier had personally decided wasn't good enough. If you want to understand how a 40-year monopoly just cracked, and why almost nobody outside the semiconductor industry has heard about it, stick around, because this story goes a lot deeper than one headline. And if you find these kinds of quiet engineering wars fascinating, you're exactly the kind of person who should be subscribed to this channel already. Let's start with why this one machine matters so much in the first place. Every advanced computer chip, the kind inside your phone, your laptop, the servers training the world's biggest artificial intelligence models, starts as a blank silicon wafer. To turn that blank wafer into a functioning chip, manufacturers have to etch billions of microscopic circuits onto its surface, patterns so fine that some of the lines are only a few atoms wide. The tool that does this etching is called a lithography machine, and it works essentially like a camera in reverse, projecting a pattern of light through a mask and focusing it down onto the wafer to burn that pattern into a light-sensitive coating, layer after layer. Sometimes dozens of times on the same chip, each layer building on the one before it with almost impossibly precise alignment. For decades, ordinary ultraviolet light was fine for this job. But as chips got smaller and smaller, ordinary light simply couldn't focus tightly enough anymore. The wavelength itself became the limiting factor. The same way you cannot paint a detail finer than the tip of your brush, no matter how steady your hand is, no matter how skilled the painter. Engineers tried squeezing more performance out of existing ultraviolet wavelengths for years, using increasingly exotic tricks like multiple patterning, where a single layer gets exposed several times with slightly offset masks to fake a finer resolution than the light itself could naturally achieve. It worked for a while, but it added enormous cost and complexity, and eventually it simply ran out of room. The solution the industry landed on was extreme ultraviolet light, EUV for short. Light with a wavelength of just 13.5 nanometers, dramatically shorter than anything used before, capable of etching details thousands of times thinner than a human hair. Here is the part that should sound almost unbelievable, and it is completely true. Building a machine that can reliably generate, focus, and control light at that wavelength turned out to be one of the single hardest engineering problems humanity has ever solved. It took roughly 3 decades of sustained global research and tens of billions of dollars in cumulative investment before anyone managed to build a working commercial EUV lithography machine. The physics alone would have been hard enough on its own, but EUV light behaves in ways that make almost every part of the process brutally difficult. It gets absorbed by essentially everything, including air itself, which means the entire process has to happen inside a near-perfect vacuum. Ordinary glass lenses don't work either, because EUV light simply gets absorbed rather than passing through them, so the entire optical system has to be built from specially engineered mirrors instead, mirrors so precisely polished that if you scaled one up to the size of Germany, the tallest bump on its surface would still only be a few millimeters high. And when someone finally did solve all of that, it was one company. The Dutch firm ASML, and to this day, ASML remains the only company on Earth capable of selling a machine that can do this. Not the best company, the only company. A single EUV machine today costs somewhere in the range of $200 million, weighs as much as a fully loaded jumbo jet, and takes multiple cargo planes just to ship in pieces to a customer's factory floor. Every single advanced chip manufacturer in the world, Taiwan's TSMC, South Korea's Samsung, everyone building the chips that power modern computing, depends entirely on ASML's supply chain. So what does that kind of monopoly actually mean in practice? It means one country's export control decision can instantly reshape the entire global technology industry. Because there is no alternative supplier to fall back on. No backup plan sitting on a shelf somewhere. If ASML can't ship you a machine, you simply cannot make the world's most advanced chips, full stop. And there has never once, in the entire history of the technology, been a viable second source to turn to instead. That is exactly what happened to China. Starting in 2019, and tightening steadily in the years since, the United States pressured the Dutch government to block ASML from selling its most advanced EUV systems to Chinese customers. The logic was straightforward on paper. Without the machine, China's semiconductor industry hits a wall it cannot climb over, no matter how much money or talent it throws at the problem. It was, by most accounts, one of the most targeted and effective single points of technological leverage any country has held over another in the modern era, precisely because it exploited a genuine monopoly rather than a mere lead. For a few years, that strategy appeared to be working. China's most advanced domestic chipmakers stayed stuck at older manufacturing nodes, unable to compete at the cutting edge where EUV becomes essential. And Chinese companies were reduced to buying up older, second-hand deep ultraviolet machines and pushing them well past their intended limits using workarounds that Western engineers considered brute force at best. But here's the detail Western export control planners may have underestimated. Blocking access to a finished machine does not block access to the underlying physics. The scientific papers describing how EUV light generation works are not classified secrets locked in a vault somewhere. They are published, peer-reviewed, and sitting in academic journals available to any researcher willing to read them closely enough. And China had one very specific advantage that almost never gets mentioned in this story. A genuine insider who understood exactly how ASML's technology actually worked from the inside out. Not from a published paper, but from years spent building the actual machine. That insider is a scientist named Lin Nan. Before returning to China, Lin Nan led light source technology research at ASML itself, working directly on the core problem at the heart of every EUV machine. How do you actually generate this incredibly difficult wavelength of light in the first place? ASML's approach, the one used in every commercial EUV machine sold anywhere in the world, involves blasting tiny droplets of molten tin with a powerful carbon dioxide laser, vaporizing the tin into a plasma that emits extreme ultraviolet light as a byproduct. It works, but it is staggeringly complex, requiring the droplets to be hit with pinpoint precision 50,000 times per second inside a vacuum chamber, each droplet individually tracked, pre-shaped with a smaller pulse just microseconds beforehand to flatten it into a pancake for maximum surface area, then blasted a second time to actually generate the light. An entire precision choreography happening faster than the eye could ever follow, repeating tens of thousands of times every single second the machine runs. Now here is the twist that makes this story genuinely interesting rather than just another quiet catch-up story. There was another possible method for generating this same wavelength of light, using solid-state lasers instead of carbon dioxide lasers. Solid-state lasers are, broadly speaking, simpler, more compact, and cheaper to build and maintain than the carbon dioxide systems ASML settled on. ASML actually tested this approach years ago, during its own early research, and ASML concluded it wasn't efficient enough for mass commercial production, so the company shelved it and committed fully to the carbon dioxide laser approach instead, the approach that eventually became the global standard, baked into every single EUV machine that has ever shipped to a customer anywhere in the world. If you're keeping track of the technical details so far, here's the simple version. So what does that actually mean? It means ASML looked at two possible roads, picked one, and walked away from the other entirely, treating it as a dead end not worth revisiting. A closed chapter in the company's own research history. Lin Nan's team picked that exact abandoned road back up. Working out of the Shanghai Institute of Optics and Fine Mechanics, under the Chinese Academy of Sciences, Lin Nan and his team began systematically refining the solid-state laser approach that ASML had discarded years earlier. Testing different laser configurations, tin droplet geometries, and timing sequences in pursuit of a number that had eluded serious researchers for years. And the results, tracked publicly through a series of peer-reviewed papers, are difficult to dismiss as propaganda or exaggeration. In December of 2024, the team published results showing a conversion efficiency of 3.42% in generating extreme ultraviolet light, essentially a measure of how much of the input energy actually gets turned into usable EUV light rather than wasted as heat. A seemingly small percentage that actually represents an enormous engineering achievement given how much energy simply disappears as waste heat in any plasma-based light generation process. For context, Europe's own Advanced Research Center for Nanolithography had only managed 3.2% in a comparable experiment back in 2019, meaning China's solid-state approach had already matched, and slightly exceeded, a benchmark set by one of the world's top nanolithography research institutions. That alone would have been a solid, respectable research result. But then, in February of 2025, the same team published something far more dramatic. A broadband EUV generation scheme achieving a conversion efficiency of 52.5%. So what does a jump like that actually tell you? It tells you this wasn't a lucky one-off lab result. It was a research program making rapid, compounding progress on a problem the rest of the industry had assumed was settled decades ago. While Lin Nan's academic team was publishing conversion efficiency papers, an entirely separate and far more secretive effort was quietly running in parallel. And this is the part of the story that reads almost like something out of a spy thriller rather than a materials science paper. Inside a high-security facility in Shenzhen, overseen by China's Central Science and Technology Commission, a different team had been assembling something far more ambitious than a lab experiment. A full working prototype of an entire EUV lithography machine. According to investigative reporting, this team includes former ASML engineers themselves, people who once worked directly on the company's most advanced systems and later left to help build a domestic Chinese alternative, bringing with them years of hands-on institutional knowledge that no published paper could ever fully capture. To assemble the prototype, the team reportedly salvaged components from older, second-hand ASML equipment, sourced additional parts through secondary markets and intermediary companies, and incorporated export-restricted components from Japanese suppliers Nikon and Canon as well. Piecing together a working system the way a restorer might rebuild a vintage engine from parts scavenged across a dozen different scrapyards. Auctions of older ASML equipment inside China reportedly continued as recently as October of 2025, suggesting this sourcing strategy is still actively ongoing even as you're watching this. A dedicated team of roughly 100 recent university graduates has apparently been assigned specifically to the painstaking work of reverse engineering individual components, piece by piece, studying exactly how each part functions and rebuilding equivalents domestically. Essentially running the world's most advanced remedial engineering course using stripped-down machines as the textbook. Internally, sources describe the effort using a name that should tell you exactly how seriously Beijing is taking this: the semiconductor industry's own Manhattan Project, a label meant to convey both the scale of national resources being committed and the strategic urgency attached to the entire program. The Shenzhen prototype was completed in early 2025 and has been undergoing testing ever since. It occupies nearly an entire factory floor, and here's the important nuance worth pausing on, because getting this detail wrong would overstate the story. The machine is operational, and it is successfully generating extreme ultraviolet light. It has not yet produced a functional, sellable computer chip. Generating the light is an enormous technical achievement on its own, but it is only one piece of an extraordinarily complex system that also needs precision optics capable of focusing that light with atomic-level accuracy, ultra-pure photoresist chemicals that react correctly to the light, and manufacturing tolerances measured in fractions of a nanometer across every single component working in. Perfect coordination. So what does that gap actually mean for anyone trying to judge how close this technology really is? It means China has cleared one of the hardest individual hurdles in EUV lithography, but not yet the entire obstacle course. And conflating the two would be exactly the kind of overstatement serious industry analysts have been careful to avoid. That brings us to the 14 nanometer chip mentioned right at the start of this video, because this is where the story moves from prototype testing into something you can actually point to and call proof. Separately from the massive Shenzhen prototype, Chinese researchers demonstrated a desktop-sized compact EUV light source, dramatically smaller and simpler than a full industrial ASML-style system, and used it to successfully produce a working 14 nanometer chip. 14 nanometers is not the absolute cutting edge of global chipmaking today. TSMC and Samsung are already mass-producing chips at 2 nanometers and pushing toward 1.4 nanometers by the end of the decade. But 14 nanometers is still an entirely respectable, commercially relevant node, used in plenty of real-world electronics currently on the market. And the significance here isn't really about matching the absolute bleeding edge. It's about proof of concept moving from a laboratory curiosity into an actual, physical, working chip that came off a light source China built using a method the rest of the industry had abandoned. So here's the pattern interrupt worth sitting with for a second. Why does a smaller, desktop-sized proof of concept matter more than the giant industrial Shenzhen prototype in some ways? Because it demonstrates the underlying physics works reliably enough to produce a real, usable result. Not just an impressive light show inside a research chamber. There's one more piece of this puzzle that rarely makes it into the more excited headlines about China's EUV progress, and it might actually be the hardest problem of all. Harder in some ways than generating the light itself. Photoresist. Photoresist is the light-sensitive chemical coating applied to a silicon wafer before it gets exposed to EUV light. And its job is to react precisely and predictably to that light, forming the actual pattern that eventually becomes a chip's circuitry. Essentially translating an invisible beam of extreme ultraviolet light into a physical permanent structure on the wafer's surface. The purity requirements for EUV-grade photoresist are almost impossible to overstate. Contamination levels have to sit somewhere between subparts per billion and parts per trillion. A level of chemical purity most industries never have to think about at all. closer to the standards used in making pharmaceutical-grade compounds than anything found in typical industrial chemistry. A single stray contaminant molecule at the wrong spot can throw off an entire circuit pattern, and multiplied across billions of transistors on a single chip, even a vanishingly small error rate becomes a serious yield problem. For years, this specific chemical challenge has been dominated by a small handful of Japanese suppliers. Companies that have spent decades refining their formulations to hit these extraordinary purity thresholds, and China has historically lagged significantly behind in this exact area. In July of 2025, though, a research team at Tsinghua University announced a genuine breakthrough in EUV photoresist development, using a chemical formulation notably different from the established Japanese approach, taking its own separate path rather than simply trying to copy an existing recipe. It's a promising, credible lab result. It is also, by the researchers' own account, still a long way from being ready for actual high-volume factory production, where consistency across millions of wafers matters just as much as the initial chemistry itself. So what does that gap tell you about the overall timeline here? It tells you that even if the light source problem gets fully solved tomorrow, there's still a second, entirely separate chemistry problem sitting downstream of it, and solving one does not automatically solve the other, no matter how impressive either individual breakthrough looks in isolation. Which brings us to the honest, sober part of this story. The part that separates a level-headed engineering breakdown from breathless propaganda in either direction. Multiple industry analysts, including specialists who've spent years tracking China's semiconductor progress specifically to avoid overhyping isolated results, have converged on a similar rough timeline. Beijing's own internal target is reportedly full EUV chip production by 2028. Several people with direct knowledge of the program have suggested that 2030 is a considerably more realistic milestone, a gap of 2 full years between the official ambition and what the engineers actually closest to the work believe is achievable. Which is itself a telling detail about how these programs tend to be communicated internally versus externally. And even once China does reach reliable commercial EUV production, most serious analysts expect the country will still be running roughly 1 to 2 full technology generations behind the absolute cutting edge. Because ASML and its customers aren't standing still while all of this happens. By the time China achieves stable EUV production, the global frontier will likely have already moved on to high numerical aperture EUV systems and next-generation process nodes that don't even exist in mass production yet today, meaning the finish line itself keeps moving forward even as China closes the distance to where it currently sits. So what does being 1 to 2 generations behind actually mean in practical terms? It means China would gain the ability to build advanced chips domestically for critical industries and national security applications, closing a strategic vulnerability that currently leaves the country dependent on outside suppliers for its most sensitive technology needs, without necessarily closing the entire commercial gap with Taiwan's TSMC anytime in the near future. Those are two very different outcomes. One about strategic independence, and one about commercial competitiveness. And conflating them is exactly the kind of mistake that turns a nuanced engineering story into an oversimplified headline. There's also a broader structural story unfolding underneath all of this, one that goes well beyond any single machine or research paper. As of January of 2026, China's domestic semiconductor equipment self-sufficiency reportedly crossed 35%, up from roughly 25% just 2 years earlier, according to industry tracking data. A climb that would have seemed wildly optimistic to most Western analysts back when the export restrictions were first put in place. That climb didn't happen through EUV alone. It reflects a much broader, coordinated push across dozens of categories of chip-making equipment, ion implantation tools, deposition systems, etching equipment, and metrology instruments. Much of it previously dominated entirely by American, Dutch, and Japanese suppliers, who had, in some cases, held comfortable market positions for decades without any serious domestic Chinese competitor in sight. Analysts tracking this shift have described Western export restrictions as functioning less like a deterrent and more like an accelerant, forcing exactly the kind of coordinated, well-funded, state-backed push that produced results like Lin Nan's team and the Shenzhen prototype in the first place, essentially manufacturing the very urgency and resource concentration needed to solve problems that might otherwise have taken decades longer to prioritize. So step back and ask the harder, so what question underneath all the individual technical milestones? What happens to a decades-old strategy of technological containment when the restrictions themselves become the catalyst for the very self-sufficiency they were designed to prevent? Zoom out even further, and this story stops being about one machine, one lab, or even one country's chip industry entirely. For 40 years, the entire global semiconductor industry operated on a quiet, mostly unspoken assumption that EUV lithography was simply too hard, too expensive, and too specialized for any second player to ever seriously challenge ASML's position, an assumption so deeply embedded that entire national industrial strategies were built directly on top of it, without much serious consideration of what would happen if it ever stopped holding true. That assumption shaped trillions of dollars in corporate strategy, national industrial policy, and geopolitical leverage for decades. It is now being tested directly, not through a single dramatic breakthrough, but through the accumulation of dozens of smaller wins, a conversion efficiency paper here, a reverse-engineered component there, a 14-nanometer proof-of-concept chip somewhere else entirely, adding up piece by piece into something that increasingly looks less like a fantasy and more like an inevitable, if still incomplete, arrival. The kind of slow, compounding progress that rarely makes for a single dramatic headline, but adds up to something enormous when you finally step back far enough to see the whole shape of it. If a technique the world's only EUV supplier personally tested, rejected, and walked away from decades ago just became the foundation for cracking their 40-year monopoly, what other technologies do you think got shelved somewhere as not good enough, sitting quietly in an old research paper, just waiting for someone patient enough and motivated enough to go back and pick it up? Let me know what you think in the comments.